Hello chemistry students, I'm going to do a little supplemental video to the video that you just watched on Edpuzzle. The video was great. Actually, the guy said a lot of the things that I would say in class if I was there with you, which I miss all of you. But I just wanted to kind of fill in a couple things and let you know. So this is a periodic table right here that has electronegativities on it. And all the electronegativity is when there's a chemical bond created, we think of the electrons as being like directly in the middle, in between two atoms. And that's not always true. It can be true for some, but it's not always true perfectly. So the higher the value of electronegativity, and if you look at the table, 4.0 is the highest it can be. And then 0.7 is the lowest it can be. So the biggest difference in electronegativity that you can have is 3.3. And if you had an electronegativity difference of 3.3, that would definitely be an ionic bond. The difference in electronegativity would be so great that the electrons would transfer. Now on the other side of that, because this is like a continuum, if the difference in electronegativity, if you have two atoms bonded together, say like a carbon and a carbon, and the two carbon atoms are bonded together, well then there is no difference in electronegativity. The 2.5 minus 2.5 is 0. So that is the most pure covalent bond, or as the video said, a non-polar covalent bond, same thing. That is the perfect sharing. This is the case where the electrons would be in the middle. So one of the things I think you missed, this is supposed to represent the electrons. And if you look at this, you can see the electrons are perfectly shared around the two atoms that are here. And if you go over on the continuum to the other side, in this case, the electrons are not shared equally. As a matter of fact, they're transferred, which is why this one's negative and this one's positive. So the new thing that you have, because this is something we've talked about before, and this is something we've talked about before, what you have in the middle is this new idea of you can have a sharing, but the sharing's not equal. That there's actually a little bit of a pull towards one atom or another. I kind of like to think of this as, let's say you have two siblings in your family, one 17 and one 16, and you only have one car to share. Is it really going to be shared equally between the 16-year-old and the 17-year-old? Probably not. One of them is probably going to have the car a little bit more than the other one. And in that kind of a family dynamic, that's what you get here going on in the middle. So this cloud almost represents the amount of time that the car would be shared, or in this case, the electrons are more here and less here. And if they're more here and less here, then this is what we call a partial negative charge. See that symbol in there? It's kind of a partial negative charge. So here's the same exact picture, just kind of spread out in a little bit different way. This is your covalent bond, your non-polar covalent bond. This is your polar bond, and this is the ionic bond. It's like king of polarity over there. And all it means when we say polarity is that there's two poles, a positive and a negative. So this symbol right here means partial positive, and this is water. So water down here, oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So we do have a difference in electronegativity. And if we took picture after picture after picture after picture after picture, this is what it would look like for where the electrons are. The electrons would spend more time on the oxygen side of the molecule and less time on the hydrogen side. And because of that, that's where you get this partial positive and the partial negative charge. Got a PhET simulation here, which also does kind of the same thing. If you look right now, here's two atoms, and right now they both have the same electronegativity. And as soon as there's a difference in electronegativity, you can see this thing kind of creeping in here. That's what's called the bond dipole. It's going to show you which way the electrons are moving, and they're moving this way, because this is more electronegative than this one. So because this one is less electronegative, it starts to become partially positive. And because this one is more electronegative, it starts to become partially negative. And the bigger the difference, the bigger the partial charge, until ultimately it does become an ionic. So the other thing that you might notice is this arrow is getting a lot bigger in between here. And I kind of refer to this end where this thing is. It's almost like it makes a little plus sign. And the little plus sign goes on the side that's more positive. and the arrow points to the direction that's more negative. So what we're showing is we're showing the direction of the electron flow. So as I make the charges, the electronegativity charges more the same, you'll see that that arrow disappears and the partial charges disappear, because right now these two atoms have the exact same electronegativity again. And if I start to make this one less electronegative than the A atom, you can see that there's a partial positive set up over here now, because the A atom is more electronegative, so it's pulling the electrons towards it, and as it pulls the electrons towards it, you can see that this charge is set up. You can also show it this way with the electron density, which I think is kind of cool. If I go right back to the middle, this is kind of like those little blue blobs that you had. Right now, the electrons are being shared equally around both of them. And if I make the electronegativity great, you can see that the electrons are more here now and less over here. So hopefully this video helped explain things a little bit better about what a polar bond is. And ready for this? I hope it wasn't too negative. Oh, okay, it was bad. Sorry. All right. Get the homework done. Turn it in. I hope you guys are all safe and doing well at home.